I was about to sleep and I just got an insight about what has happened with feature engineering. When all of us started learning AI and we were in our initial days, we heard of something known as feature engineering. All the classical machine learning algorithms like decision trees, random forest, any sort of ensemble, linear regression, logistic regression, these algorithms required us to give them a certain feature vector, right? And that feature vector was nothing but a representation that is produced or that was produced by a different algorithm, right? So for example, if I need to give my logistic regression algorithm a way to recognize cats and dogs, and I have 5000 images of cats and 5000 images of dogs, I would convert all of those pixel values into a certain feature vector, which sometimes I can call it a histogram of oriented gradients, or I can call them something else depending on what feature engineering did I do. So I used to deal with the data as part of my whole machine learning workflow, and dealing with the data required me to clean the data, to get the data ready for the algorithm, and to do feature engineering on it. So feature engineering was basically converting the raw data into from its original modality to a representation, to a statistical representation that is helpful for the model in order to build or in order to do statistical pattern recognition, right? This was the whole classical machine learning workflow. So to summarize, raw data modality, a lot of feature engineering that produces representation and give that representation or the feature engineered vector to the classical ML algorithm. That classical ML algorithm will produce some results, and it produced better performance because the performance was tightly coupled with this feature engineering strategy that we used. Now when deep learning was introduced, even till artificial neural networks or deep neural networks, we were doing this feature engineering, right? But when, especially when deep learning was introduced, and when we first saw computer vision, when we first saw convolutional neural networks, right? What they did, they said, don't produce any static representation, don't produce any static embeddings, don't produce a feature vector before you give it to me. Consider me as an algorithm that can do the feature engineering for you, right? So the feature engineering that CNNs will do is not going to be static, right? It's going to be learnable. Now what changed? Previously, all the feature engineering that we used to do was frozen and then fed to the algorithm. CNN said, no, I will not freeze the features. I will not freeze a feature vector. I will take in raw input, as in I will take in the raw images as pixel values. I will produce a feature map, right, based on the number of kernels that you give me as hyperparameter, based on the size of kernels that you give me as hyperparameter. I will convolve all those kernels, do the feature engineering myself. Now, all the feature engineering that CNNs will do as part of their training, not inferencing, as part of their training, is going to be dynamic in nature, right? When I say dynamic, I basically mean that CNN is not going to use a special algorithm to do feature engineering. CNN is going to use its own architecture, produce a feature map internally while it trains, and that feature map will evolve. Why, when we say it evolves, we simply mean that at the start of the training, CNN might have a random feature map. As it progresses down the training, the feature maps is going to evolve because all the kernels that are producing the feature maps are learnable. Now, how will it evolve? It will not evolve based on some human interpretation, based on that these features look good, so let's preserve them, based on some other representation. It is going to evolve based on the loss function, right? So, if CNN is doing cats versus dogs, it's going to produce a feature map internally or multiple stacks of feature maps internally that are best to classify cats versus dogs, right? So it's going to evolve with respect to its loss function. If the loss function is cross entropy loss and CNN has to perform a certain task, so the feature maps are going to evolve, or the features internally or the kernels of in a CNN are going to be learned based on what is the task that is to be performed, right? They're going to be tightly coupled with the loss function, right? Now think about transformers. The same happens. Transformers, before transformers, we used to tell any NLP algorithm or any classical machine learning algorithm that I'm producing a static word to vector embeddings. These are my static embeddings. Use them to build a classifier or to build a next token predictor. Transformers, has a narrative. They simply tell us that don't think about feature engineering. Let me produce a feature vector. Let me produce the understanding of a language using token embeddings, using an attention mechanism, right? Token embeddings will help me understand or model all of these words better, all of these tokens better internally, and I will produce the contextual relationship between these tokens in order to understand the language better, and my in order to understand the language better with respect to next token prediction, right? I will produce a representation internally that is going to help me do the next token prediction better, right? I will start with a random embedding. I will start with a random feature vector, right? I will start with a random contextual representation, and I will keep on evolving while training as and when I, decrease my loss for next token prediction, so that internally I am a network that produces the best representation for X task. I produce a best representation on Y modality for X task, right? So all deep learning is doing is internally it's producing the best representation given the data and given the objective function, right? So it simply is telling us, give me the raw data. Don't do static feature engineering. Don't freeze the feature vector and then feed it to me. And don't think of me only as an output head. Think of me as your feature engineer plus an output head that can do certain classification, certain prediction for you, right? And it was going to do the classification and prediction for you based on the feature vector or the feature map or the representation that works the best for that particular task, right? So CNN, if we think about it, does CNN really know, given image A and image B, which is the best feature vector that it has to produce? No. CNN automatically learns internally the feature maps. The feature maps it produces is based on the kernels, right? So it learns all the kernel values. All the kernel values it learns are based on our objective function, right? So if our objective is to classify cats versus dogs, it's going to learn the best kernel values that produces a certain feature map that are good for classifying cats versus dogs. Same for transformers. If the task for a transformer is to do next token prediction, it's going to produce a token embedding for each token, right? And learn the token embeddings in such a way, and learn the contextual representation in such a way that the learned representation helps a transformer produce the best next token prediction, produce the best contextual and coherent text, right? So the learning of these features, or the producing of these features while training, not while inferencing, is very tightly coupled with the objective function, right? It's not random. It's not that, with human interpretation these features look good, let's preserve them. With certain parameters that these features have a certain depth, so these features are 512 dimension, let's preserve them, right? No, the features that are preserved internally in the algorithm are determined at training time, right? That's why static feature engineering, feature engineering as a separate algorithm before a neural network is, or before a classical machine learning algorithm, is more or less encapsulated under deep learning. All the deep neural networks, no matter what modality we are solving for, internally produce a feature representation themselves based on a certain objective that they are trying to accomplish, right? And all of these things are learnable. They are not static. They are produced just in time. They might start with a random representation. Over time during the training phase, they keep on learning these representation inherently and produce the best statistical representation in higher dimensions that is best usable for the objective function, such that the loss also gets minimized. Cheers. I hope you understand this insight and the mental model, and we'll talk more about it in the future videos. Thank you.